Hi everyone, I'm Vigovszky, and I'd like to talk a bit about generating these libraries, or generating libraries in general. Well, okay, so I would rather say generating functional wrapper libraries. And what I mean by that is that you have some kind of Scala code, some functional Scala code, and you may have some kind of existing Java library that you want to use, or external systems like AWS, Kubernetes, or anything else, or maybe just your own services that you want to interface with by gRPC, HTTP, or whatever else. So wrapper libraries for all the different kind of these third-party systems. So why would you write a library to work with these? And I will primarily use Zio examples in this talk, but it's a bit more general. But why would you do that? First of all, to reuse boilerplate, so you don't have to copy-paste all these, wrapping things in effects and converting data types and all this kind of code you don't have to use every time or do every time you are interfacing with these systems. The other reason is to make it easier to use to maybe other members of your team, or to easier to reuse these systems in next projects. And the third reason is that you can take advantage of your effect system, extra capabilities like streaming, the Zio modules, and so on. But what I really want to talk about is a subset of these libraries that can be generated automatically. So let's say that we have some kind of machine-interpretable schema, any kind of schema that we can transform somehow to source code. One advantage that we get is that basically we have, once we do this, we have free updates forever. But of course, forever means that we have free updates until the original assumptions that we had about the schema are still true. And the other thing we get is basically 100% full API coverage, almost 100% full API coverage if we do it right. So we don't have to think about what subset of our external system we want to wrap and then figure out in the next project that we just missed exactly the thing that we need in the next project or in the next iteration of our project. I will use the two mentioned libraries as examples, Zio AWS and Zio Kubernetes as examples. Both are libraries that are generated, and I created them in the past 1 or 1.5 years. In the case of the AWS wrapper, it's built on top of the Java SDK, the Java V2 SDK, and the machine-interpretable schema in this case are AWS-specific JSON files that are embedded in the Java SDK's artifacts as resources. There are a couple of JSONs. I don't think they are following any kind of standard. I think it's an AWS-specific thing. They are just JSONs that are describing the operations of these services and the data types involved in these. In the case of Zio Kubernetes, it's having its own OpenAPI specification. It's a standard way to describe HTTP endpoints and data types. So that's what Zio Kubernetes is generated from. Also, I have to talk a little bit about some drawbacks. And one thing that you may say is that, OK, this is really nice, but you can come up with a much better higher-level API if you are not directly following these schemas, but thinking about it and adopting it to a functional way of thinking and so on. But I would say that it's still better to first generate, if possible, these low-level APIs that are directly mapping to the underlying schema, and then build a higher-level API on top of this. And a good example of it is Zio DynamoDB that you could heard about yesterday, which is also written in this way, that the API calls are the generated Zio AWS library, but it provides a much nicer API on top of it. And the other problem is testability. So you cannot handwrite test cases or test suites that are providing a full coverage to your generated library because it depends on the schema. And one possibility here is to try to generate the test suites as well, but this is not always possible or not easy. And I have an example of this problem. In the first version of Zio Kubernetes, I assumed that the delete operation on resources is always returning the status data type of Kubernetes, because every example I checked and everywhere I looked in the scheme, it was like that. And we released the library like that, and for, I don't know, maybe half a year, nobody noticed that, in fact, not all the resources are having this as a result type for the delete operation, until finally someone tried to delete something that is in that category, and then it blew up. So yeah, the reason for that bug is that I was using, or not using the schema for figuring out the return type of the delete operation, but hard-coded status. And the fix is to use the schema for everything that it describes. Okay, so I hope that you are now a bit convinced that code generation makes sense in some cases. Let's see how we can generate code. And I will use a very simple example in this section. Let's say we want to generate this code. We want to generate a set of case classes with fields, and we want to generate a dump function in them which just prints these case classes to the console. And the first thing to do every time is to find out a good model for your code generator. So one possible model that describes this problem is that we have a type called type, not Z type. And it can be a primitive or a product type, and if it's a product type, then it has fields, and the field is a mapping between a field name and the type. And once we have this code generator model, we can use it to describe the thing we want to generate. And this example describes the code that was shown on the first code snippet, the two case classes with a couple of fields. So once we have this model, how can we transform it to source code? First obvious choice or idea is to use a string builder or something similar, which may seem a very simple solution. You are just concatenating strings. You are traversing your model and calling these append functions. It's simple, and for very simple cases, probably a viable choice. But it's non-composable. It doesn't give you any type guarantees. And for large code generators like the AWS or Kubernetes generators, it wouldn't be scalable for that scale. So fortunately, there are a lot of ways to improve this. And the first direction we could take is to use some kind of templating library, templating language. And on this code snippet, I'm showing a liquid template example. And that's a template language that I was using for code generation for a long time, for quite big projects. And one advantage for using this is usually it gives you a much more readable way to describe what you are generating, especially if what you are generating has larger static blocks. So it's not like every line is a template control structure, but some kind of Scala code or something that we want to see in a wall. But on the other hand, it's quite redundant. Usually these template languages are not powerful enough to express like reusability, like composition. You cannot really inject these fragments into each other in any way, and no parametricity and stuff like that. For this particular template language, there is a Java library called lickp that you're using, and yeah, this is an example that it's a Java library, and it should also have a functional Scala wrapper, but that's another question. And I just wanted to point out that if your template engine supports something like this library, like strict variables, which means that it fails on the first missing thing from the template, then you should definitely turn that on. Otherwise, it will just emit empty strings or something worse into your tens of thousands of generated code. And you have to figure out why. And another problem with the template-based approach is that I think basically this approach requires you to build up an intermediate template model, which is specific to the template engine itself. For this lickp library, it's a nested hierarchy of Java maps. And this means that you have your code generator model, and you have to transform your code generator model to this intermediate template model first, and then use the template engine to generate the source code. And this means that your code generator logic will be split into two halves, and one half is when you are transforming the model to the template model, and the other is the template control structures. And this makes it a bit hard to maintain if it goes too big and complicated. Another possible direction from the string builder would be to use some kind of pretty printer library. And what I mean by pretty printer library here is that you are having some kind of composable pretty printing blocks that you can use to build bigger and bigger composable blocks from. And once you figured out the correct pretty printing blocks to work with, you can generate your code with them by using different kind of combinators. And this is somewhat readable. So if you are choosing your blocks correctly, then it might look like the target language a bit. And it's composable, but still you are just under the hood, just concatenating strings. So you have no guarantees that what you are doing is a valid Scala code or anything like that. So the next logical step is to not generate strings, but generate something else. And this would be the abstract syntax tree of the target language. And the target language in this case is Scala, and the Scala method library provides an implementation of the Scala syntax tree. And this looks like exactly the other examples you've seen yesterday on multiple targs, because it's just the same Scala AST, just a different implementation. A Scala method library provides a pretty printer for this AST, so if we can generate this tree of nodes, then we can just use its built-in pretty printer to provide to produce the source code. It's fully composable and the typed way to construct the Scala code, but it's completely unreadable if you are doing it this way. So if you are building directly the trees, there is no way to, just connect it in your mind with what you want to achieve. But fortunately, there is a way that basically combines the advantages of templating and the AST approach. And this is the quasi-code support of Scala Meta or other similar libraries. And it gives you a readable, but still composable and type-checked way to build up Scala code. So you are having these string interpolators that are parsing compile time your Scala code snippets, and it supports injecting them into each other. So in my opinion, this is the best way to do this, but it's still too low level for code generation purposes because of some issues that I ran into. And one of them is that you have to work with these Scala node types like terms and types and selectors, as you've seen yesterday, selecting from a package. Sometimes you need a term, sometimes you need a type, sometimes you want to select it from the package, sometimes the package is already imported and you only need the identifier. And it's a bit hard to maintain this in a way that if you need to change the code generator, this is not breaking. And the other problem is how you maintain your imports list of the generated files. If you are not importing anything but using fully qualified types everywhere, then your generated code will be unreadable. And people are reading the generated code because that's how they figure out what your library is doing. So I created a small wrapper on top of Scala Meta, which I'm calling Metagen. It's really like a very small library. It just defines a package and the Scala type, which are higher level ways to describe a package or a Scala package or a Scala type, and they have methods to convert them to the different kind of Scala meta nodes, like terms and types, fully qualified types, and so on. And another thing this library is doing is that if you are using these higher level types everywhere when you are working with types, so for example, in the middle code snippet, you can see that the dump function has even the ZO type of it, the ZO console IO exception unit is written by these higher level helper functions or helper values. And the reason for that is that it will force you to use fully qualified types everywhere, and after that, the metagen's extra step in the code generator will generate your import list automatically, so you don't have to deal with it, and you don't have to maintain the import list when you are renaming things or moving things in your generated code. And it also provides some helper functions to run this whole thing, to run the generator, run Scala format on the output, and save it to a file and specify the Scala version. So like some convenience wrapper around the whole thing. All right, so how you should generate code? My short answer is build a good model for it first, use Scala meta with quasi-coding, and when you are dealing with packages and types in your model and in your Scala meta snippets, then use this abstraction of metagen. All right, so now that we know how I think we should generate code, let's see what you should generate. And one thing you should generate, probably every time, is the model. As we are generating a functional Scala wrapper, this should be ADTs. You should generate case classes and seal traits, no matter what the underlying Java library is doing. And in many times, you want to generate converters. For example, in ZOAWES, we are having these underlying Java objects, classes that are describing all these model types. And there are converters from these and to these generated automatically for your Scala ADTs. In other cases, for example, in ZO Kubernetes, you want to generate codecs like JSON codec in this example that will serialize your data types in exactly the way as your schema was describing it. And sometimes these schemas describe primitive types, and you can consider generating types for like new types wrapper for them as well. It's not something that any of these libraries are currently doing, but it could be, and I'm planning to. And finally, I wanted to mention that if the schema contains some kind of descriptions for the fields and data types, then you should consider generating comments as well, because as I said, people will read the generated library, and it helps a lot to understand how it works. The next topic is generating the ZO layers or modules. And just to mention these two examples, in ZO AWS, I decided to generate a ZO layer for each AWS service. For example, EC2, Elastic Beanstalk, S3, as you can see on the screen. But in the case of ZO Kubernetes, I decided to have one module per Kubernetes resource type. And I think this is a nice way to represent this, but soon we realized that if you are having a function that are using 25 different kind of Kubernetes resources, then the type signature is a little bit scary. So it's now also providing one unified layer, which is called Kubernetes, and it gives you access to all the resources if you are not interested in this way to exactly specify what you want to access to. And my main point here is that as you are generating the code, you can relatively cheaply, almost free, make these kind of choices to generate multiple interfaces if you want to, but be careful to only do it if it really makes sense, and not just because you can generate arbitrary number of different representations for the same thing. So once we have layers and models, we should have some effects that we can call. And for ZO AWS, as I said, it's built on top of the Java SDK for some reasons that I didn't want to talk about. Anyway, so it's a Java SDK, and it's returning Java futures. So here our job to convert these Java methods into ZO effects, and it's really easy because we can use the ZOs from completion stage constructor. So we are converting the data types from the Java model to the generated ADTs, and we are using ZEO's constructors to wrap the Java feature into ZEO effect. In the case of ZEO Kubernetes, it's not built on top of any kind of Java library. It's talking with Kubernetes by HTTP directly, and I was using STTP with the ZEO backend here, and this means that the STTP request sending function itself is a ZEO effect, so nothing to do here. So in more general, if you are doing this, one possibility is to use a native ZEO library if there is one. Or you have to convert your functions to ZEO effects, and you can do with synchronous APIs with the ZEO attempt, or APIs with callbacks with ZEO async, Scala features with ZEO from future, and so on. And there are a couple of interop libraries to wrap even more things in a very convenient way to ZEO. And the last thing I wanted to mention is streaming. If it makes sense, I think it's a really nice thing to do to also generate streaming APIs in these wrapper libraries. For ZEO AWS, it's basically generating a streamed API, a ZEO Stream API, for everything that is supporting pagination or working with input or output or byte streams like S3 upload and download. And there are a couple of event streaming API calls as well. These are all getting ZEO Stream. These are all exposed as ZEO streams on the generated API. And in the case of the Kubernetes wrapper, it's having a watch streams, which are infinite stream of events of the underlying Kubernetes resources. And finally, I have 3 more things, like tips that I collected from these libraries that I think makes sense to consider when creating such libraries. And the first one is aspects. And aspects are functions that are transforming effects. And in the context of code generation, I think it's a really nice way to somehow modify the core implementation of your wrapper. In this case, it's used for ZEO AWS. And as you can see, you can take one raw AWS service like DynamoDB and apply aspects on it. In this case, we are applying an aspect that is doing call logging, and another one is doing circuit breaking. But it could be any kind of thing that if you apply it to an effect, it either just taps it and does logging or metrics or retry logic and so on. But here we are applying it to the whole service and not to an effect. And what it really does is that it will use these aspects every time it is doing one Java SDK call. So it moves it down to the core and applies it just on the single effect that is calling your Java SDK. So you can, this way, inject your custom logic or custom retry logic and logging and metric stuff into the Java core. For example, when it's doing pagination and calls the Java SDK several times while you are running a ZEO stream, it will apply these aspects every time it's reaching out to AWS. So I think it's a nice way to interact or to make customizable things in your generated libraries. Another topic is optionals. First version of ZEO Kubernetes used the normal Scala option type for everything that is optional in the OpenAPI schema. And then it turned out that almost everything is optional in the OpenAPI schema. So it was a really painful thing to use when you wanted to build these data types of Kubernetes, like a cluster role binding. In the original version, you had to use the sum constructor basically for each field, and it was very unreadable and inconvenient. And then we came up with this alternative optional type that is used in ZEO Kubernetes, which is almost like the normal option type, but it has an implicit conversion from the underlying type it's wrapping. So when you are building these models, you don't have to use the sum constructor. It's just a very little convenience feature, but I think it makes a lot of difference. This way, these Kubernetes resource specifications look almost like when you are using YAML, but it's type checked, so it's better. And finally, I want to talk a few words about also generating mocks or test implementations for your stuff. So in general, to think about testing when generating these libraries. So for example, Zio AWS generates Zio test mocks for each service, which is something that is possible with a macro as well. But there is no need for macros, sorry, Kit. Because we are already generating code, so we can directly generate it into the source code, which makes it even more discoverable and probably a bit more environment friendly. So yeah, why not? You can generate the mocks. And in the case of Zio Kubernetes, you are, I'm not generating mocks, but some kind of alternative test implementation for all the resource types, which is an in-memory representation of the Kubernetes resource that you can use in your tests. And I think that's it. So thank you for your attention and allowing me here.
Thank you so much, Daniel, for a fantastic presentation there. So I think we had one question from the internet, and then we'll give everyone else a chance, which was essentially, it seems like you've talked about a bunch of techniques for if you're going to create your own generated library, here are some techniques for you. Do you think there's a role for a library that focuses on these tools for generating other libraries?
Yes, I felt so, and that's why I created this string wrapper on top of Scala meta. It's something that is really new, so I'm only using it in the AWS generator, not in the Kubernetes yet. And it's like still a thin wrapper on top of Scala meta, but it could evolve to something that provides more functionalities to this topic. Yes. All right.
Well, maybe a topic for a future talk or a symposium session. I think we got one question there.
Just the GitHub, is there a GitHub for that?
Yes, I will post it into Discord or somewhere.
Okay, thank you.
One more. Oh, maybe two more.
A quick question. What do you feed in to, for example, the AWS code generator? What goes inside?
Yeah, I'm feeding in those AWS specific JSONs that I mentioned here. So each AWS artifact coming with the Java SDK v2 contains some kind of JSONs like this service2 JSON, paginators JSON, and so on. And this, so I'm depending on the Java SDK, reading the resources and interpreting these JSONs.
One more question from the internet, this one from Eagle. Is the SBT project that compiles it as a library also generated?
Yeah, I originally wanted to talk about the SBT part as well.
The problem with a half-hour talk?
So for AWS, the SBT, so in both cases, the code generator itself is an SBT plugin. I didn't mention that. I think SBT has a really nice support for code generators. But in the case of AWS, even the SBT projects are dynamic because it depends on, AWS is coming up with a new service every 2 weeks, I guess, or I don't know. So it's also generated. So SBT has this feature that is, I think, called dynamic projects, or I don't know what. But in the plugin, you can generate additional or add additional projects to your state. And this is how it works. There is one artifact that describes all the existing AWS services. And with reflection, I'm looking for all the services and all these JSONs and generating all the projects dynamically in SBT. And it requires about, 10 gigabytes of memory to just compile.